Swayam Prabha. Digital India. Educated India.
Introductory part which will be required for your machine learning. So I have designed the slides in a little bit different way than you will find in your usual course on linear algebra. So the plan for this, I have actually 3 lectures today, 2 lectures, and Thursday morning another lecture. So basically, I will be covering in each of these lectures one of the topics. The first is today our goal will be the fundamental theorem of linear algebra, the part 1. So basically, we'll be understanding the vector space, the subspaces, and the 4 important subspaces which will be we need to understand their the relations and the dimensions, right? So that is the fundamental theorem of part 1. Then the next lecture, after the second lecture today, we'll be learning the orthogonality. So basically the geometry and relations between those fundamental subspaces, 4 fundamental subspaces. And in the next Thursday's lecture, I will be covering the climax of linear algebra, you can say. So that's the final part of the fundamental theorem, which will give you a singular value decomposition. So which is required to decompose a matrix into the important part and the less important part. So we'll start the very basic of linear algebra today, which most of you have perhaps seen. At least if you have studied the prerequisite, which I have asked you to be perhaps the organizers communicated with you. So we'll recap some of the things which will be prepared for the whole course today. So the vector spaces and the subspaces. Okay. So why we study linear algebra, first of all? So what's the motivation behind studying linear algebra? So you will see in many problems from applications, it basically boils down to a system of linear equations. Right? So a system of linear equations will look like this. In the matrix form, we write it in this way. Okay. Okay, so as you can see, this is a system of linear equations where we have m equations with n unknowns, right? And we can write it in this matrix form. So I'll be using the same notation throughout this lecture. A will be a matrix of size m by n, and this x will be the column vector. X1 will be xn, and this vector v will be also a m-dimensional vector. Right? So x is n-dimensional vector. I'll be using this notation. V will be the m-dimensional vector. So what we want to understand in linear algebra is the solvability of such equations. Whether we will get a solution of such system of linear equations or not. So that actually leads to the question whether the system is consistent or inconsistent. Consistent means it will have a solution. Inconsistent means it will not have a solution. So that's the first question we ask. What the second type of question we ask? If there is a solution, whether the number of solutions are finite or infinite. Okay, so that's the second type of questions we ask. So to understand such answer such questions, we can look the system of linear equations in different ways. First, we can look the matrix as some array of elements, a two-dimensional array of elements, or we can. So the more effective way, what we try to learn in linear algebra is to look the matrix as column by column. So that's the column picture. So this is the most efficient way of understanding the nature of solution of this system of linear equations. So we can express the equation in this column form. So each of the columns I have denoted by this vector a1, a2 to an, right? And we can express this. So what is this called? On the left hand side is the, so we haven't yet learned, but what is this called? Is the linear combinations of those column vectors, right? Is the linear combinations of these column vectors. So to understand whether there is a solution, of this system of linear equations, we have to check what we need to check. We need to check whether there exists at least one such linear combinations of these vectors which is equal to the right hand side vector. Or in other words, we have to understand, we have to find such x1, x2, xn, right, which will give us this right hand side vector v. Okay. So that's the first type of questions. So if there is a linear combinations of some x1, x2, xn, so that the left hand side equal to the right hand side. Now the another question to understand it more effectively, we want to see that whether this system has always a solution or not. Whether this system has always a solution or not. So for that, what I need to see that, so the B vector is in the space Rn, this m-dimensional vector. So if for any such x1, x2, xn, so the vector lies in Rn, then we can say that whether there is always a solution or not. So we'll try to understand this, but what you can see from here that we are not only looking at the column vectors of the matrix, right? But we are looking the span. So how these vectors, the column vectors, are actually spanning the space, what space it is generating. So that will actually lead you to that answer, that whether this will have a solution or not. So for that, you need to understand the basics of the vector space, how one some set of vectors will generate, how much space it will generate. Okay? So this will give you the answers of such kind of questions, so that we ask in the linear algebra. So for example, if you consider this example from your book, so the book, I think I have referred to that book by Gilbert and Strang from where I'm preparing the slides. And mostly I'll be taking the materials from that book, so you should follow that book. I have also referred in the prerequisite, you should follow that. So for example, in this AX, the matrix A is given by this 1, 0, 4, 3, 2, 3, and so the linear combinations of AX will be spanning this space, which is this plane, right? This plane. So we'll come to the actual definitions of how we will be getting such plane. But if you can intuitively see that that if B vector, which should be on the right hand side of the system, which is not given here, if it is lying on this space, on this plane, generated by this x1 into a1 vector, x2 vector, so then we will have the solutions x1, x2 for that particular linear combination. Okay. So basically the goal will be to understand how this set of vectors will be spanning that space, and so the dependency of those vectors, so that we know that actually what will be the dimension of that underlying subspace, what it will be generating. Okay. Sure. Okay, I'll not go into the details of the definition. I think most of you have seen this, the definition of the vector space. So what is the vector space? We also need to consider a field on which the vectors will be defined, right? And so basically the most important is these two operations that they should satisfy. The set of vectors to satisfy these two operations. So the first one is the vector addition. So if you add two vectors, they should be again generating another vector. And if you multiply by this scalar one vector, so that will be again a vector. So this is kind of the two operations will be considering in a vector space. So if they should also satisfy the 10 more conditions that you will find in any standard book. So I will not go into the details of those 10 conditions. So like the associativity, commutativity, then existence of the zero vector, existence of the inverse, right? So there are 10 set of conditions, but those are most kind of common. What I'll do, I'll just go and give few examples of different vector spaces what I'll be using here in this lecture. So the first type of vector space what we'll be mostly using is the Rn. Rn is the n-dimensional Euclidean space, you can say. So a point in Rn will be of this form, right? So for example, if you want to consider a R2, say we consider this is our vector space, and I consider a point say 2, 1. So a vector say 2, 1, say 1, 2, 1. So this is my 2, 1 vector, right? So I'll be denoting this by this vector. So this is starting from the origin to that particular point. And say I consider another vector. Say minus 1, or I consider minus 1, and then 1, 2, minus 1, 1, 2. So this will be my vector minus 1, 2, right? So you know that what will be the addition of these two vectors? So if we do the addition of these two vectors, will be 1, 1, 3, 1, 3. So 1, somewhere here, right? 1, 3. Right? So you know that this will satisfy this parallelogram law. So if you just make this, so we'll be getting this will be your 1, 3. Right? So this is in the vector space R2. And if you want to multiply by a scalar, so suppose I want to multiply this 2, 1 by a scalar say 4. So what will be that? So 4 times, right? So this is my 8, 4. So I am multiplying by 4. So this is my, okay. So this is the kind of the vector addition and the multiplication will be considering for this vector space R2. So I have written here for the general n-dimensional vector space Rn, so which will satisfy this vector addition and the scalar multiplication. So one thing that this notation of the column vector sometimes little bit it's taking too much space, right? So what the notation I sometimes use is this vector. V1. So using this notation in the first bracket, right? So order the set of real numbers, and the corresponding row vector. So any vector from Rn will be called a column vector. And that will be denoted by either that notation or this notation. And the corresponding row vectors will be denoted by this notation. So this is the notation convention I'll be using for the rest of the lectures. So not only from so the type of the vector space you have just seen is just one type of vector space, but my vectors may not be always like what you have just seen. It could be coming from the space of matrix, like the same is the vector space where we consider the vector space of all real 2 by 2 matrices, right? Or it could be from the set of polynomials of degree n, or it could be a vector space of all real functions. So the addition and the scalar multiplication operations will be defined on that particular space, like addition of two functions here, addition of two matrices there, additions of two polynomials there, and so this is for the trivial vector space because this is the notation Z actually will represent the zero vector space, which will contain only the zero vector, okay, of that particular vector space. Okay, so this is also called the trivial vector space. So, but mostly we'll be using that vector space what we have just seen, the Rn or Rn, the Euclidean vector space. So our goal is to understand different subspaces of the vector space. So subspaces, vaguely you can think of the subset of vector space, which will again be a vector space. So it will again satisfy the properties of the vector space. More formally, so what we will do, so if we are given a set of vectors, but it will always contain the zero vector. It should always contain the zero vector, unless and otherwise it will not satisfy the properties of the vector space. And if you consider two elements from that subset, then their addition should be again a vector, and that should lie into that subspace. And if you consider the scalar multiplication of any vector from that subset, that will again be in the subspace. For example, if we consider this, if we consider a three-dimensional vector space, the dimension I shouldn't use because I haven't defined the dimension, but R3, we are considering say R3. And suppose we are considering this one subset of this R3, which is a line passing through its origin. Passing through the origin, a line infinite being extended. And so will this be a vector space? Will this be a subspace of the R3? Yes, right? Because it will satisfy all the properties of the vector space. Now, if we consider another line parallel to this line, will this be a vector space, a subspace? No, right? It is not passing through the origin. Okay. For this R2, suppose I consider another. I consider this subset, this one quadrant. Will this be a subspace of this vector space? Yes? No. No. Yes? Sorry? Yes. So if you consider any point, any vector here, and if you multiply this with some negative number, right? Say minus 5 or something, right? So it will be coming here, but not in this particular space. So it will not be a vector subspace of that R2. So these are few examples of subspaces. Okay. So now we want to define one important operation based on this vector addition and the scalar multiplication, which is called the linear combination of the vectors. So if you are given a set of vectors, you are given a set of vectors, and now if you are given a vector v, we want to check whether this is a linear combinations of a set of vectors. So if you are given a vector v, we want to check whether there exists some x1, x2, xn, which will give you that particular vector v as the linear combinations of the set of vectors. For example, if you want to check this vector, say I take one vector 1, 2, 5 in 3 dimensions, and we are given a set of vectors, say 1, 1, 0, 0, 1, 0, 1, 0, 0. So you are given these 3 vectors. So you want to check whether this vector 1 to 5 is the linear combinations of this set. So will this be the linear combinations? No, right? Because you won't be able to generate this 5 because all the 3 components here are zeros. So this is not the linear combinations of the given set of vectors. But if you consider say another say 1, 0, 0, 0, 1, 0, the standard one, 0, 0, 1. So then you would be able to generate. Right? So that's how we will decide whether a vector, given vector, is a linear combination of a given set of vectors. Okay. So we have already defined the subspace. So if you know that a subspace containing 2 vectors at v and w, so it should contain all such linear combinations of v and w. If a subspace contains 2 vectors v and w, it should contain all the linear combinations. Otherwise, it will not be you will not be able to verify that will be a subspace. So it should contain all the subspace. So we want to check what's the smallest subspace given a set of vectors. What's the smallest subspace which will contain a given set of vectors? So we will define this by the span. So span of a set of vectors is the smallest subspace containing those set of vectors. So let S be a set of vectors. Okay. Then span, the linear, we will be denoting this by L of S. We will be denoting this by L of S, which is the all linear combinations of those set of vectors in S. Okay. So S will be called the set of generators. The set of generators, and LS will be the linear span. And can you first check that whether LS is the subspace of V? So V, okay, I have used the wrong notation here. VR, it should be this data. But how can we check that LS is a subspace of V? What we need to do for that? So we are given a set S, say, of say V1, V2, Vn, which are elements of the vector space, say VR. It's general vector space. You can take whatever you want.
So the linear span of this set S will be denoted by L of S, which is equal to say C1 V1 plus C2 V2 plus Cn Vn, such that Ci belongs to the scalar, right? So this is my linear span. Okay. So we have to show that this is a subspace of V here. This is a subspace of V here. What we should do? We should take just two elements from this linear span and take two scalar from the scalar field and show that their addition is again into this subspace and the scalar multiplication is again into the subspace. In other words, what you can do, you can also take two scalar fields, two scalars, and then show that, say, I consider two vectors, say, V, two vectors, V from LS and W from LS. Okay, and show and take two scalars, say C and D belongs to R, and show that CV1 plus to show plus DW belongs to, right? That should be sufficient. So you have to take this V and W into this form and show that their addition will be again into this subspace. I think you can do it yourself. I just maybe just write one line. Say V1 we consider. Say V we consider as C1 V1, C2 V2, Cn Vn. W we consider as the C1 dashed V. This is not a. All these are vectors. So when I use the underline, that's a vector. V1, C2 dashed V2 plus Cn Vn dashed. Right? And the rest is easy. You have to just show that what is your C into V plus D into W equal to C1 D C1 dashed V1. Last term will be CCN DCN dashed Vn. This is a linear combinations of those vectors V1, V2, Vn, right? So this belongs to this. So this proves that this is a subspace. Simple, but you have to just write it down. Okay. So how to prove that this is the smallest subspace containing these vectors? Smallest subspace containing this set of vectors V1, V2, Vn. So we consider any vectors, any subspace containing these vectors V1, V2, Vn. So any subspace containing this V1, V2, Vn, and then show that is containing here this linear span of S. So if you consider, just to give you some hint, consider let W be any subspace containing S, right? So W will then contain the linear combinations of these vectors in S. What you have to show that this W, so LS is a subset of W. So if you consider any subspace which is containing S, then you show that LS is contained in W. Okay. So that will be the proof for that LS is the minimum or the smallest subspace containing this set of vectors. Check. How to check this? You take an element from LS, and show that that is containing in W. So that is the proof, right? So I'll not complete, I'll just leave it for you to check if you write it down properly. So now we have understood that given a set of vectors, what is the smallest subspace this will span, right? So that is my linear span, or the linear span of those set of vector sets. Now we have started with that matrix and that system of linear equations. So what will be the similar linear span of the column vectors of that matrix? What I have shown, this matrix A. So that is the column space of, that is called the column space of the matrix A, right? That's the column space of the matrix A. So linear span we have seen. Now instead of S, if we consider the column vectors of the matrix, that is the column space, or denoted by CA. Similarly, for the row vectors, if we consider row vectors of the matrix, so this will be the row space of the matrix. The linear span of the row vectors will be the row space of the matrix and will be denoted by CA transpose. So I'll write it down again. So CA will be denoting this again and again. So please note it down. The linear span of the column vectors of A, and CA transpose. You are familiar with the transpose operation in the matrix, right? Linear span of the row vectors of A. So this is the column space. Column space. This is the row space. So basically, for finding the solvability of a system of linear equations, we need to understand these two vectors, these two subspaces. So both of these will be the subspaces. So this will be, the CA is the subspace of which vector space? CA is the subspace column. So columns are of, from the Rn. What is the dimension? So A is our m by n matrix. The columns will be from Rm. So this is a subspace. CA is a subspace of Rm. CA transpose is a subspace of Rn. So we have found two subspaces. I had talked about the four fundamental subspaces we have to understand in the beginning. So we have at least found now two. So these two are very important subspaces. We need to understand two more, but let us see some properties here. So the property one, we have already seen that CA is a subspace of Rm, and CA transpose, that the row space is the subspace of Rm. Yes. Okay. So we'll go to the what is it? n, right? 1, yeah, 1, 2, right? 1, 2, a, 2, 2, a, 2, n, a, m1, a, m2, a, m1. This is my matrix. So I showed in the very first slide, right? So what is my column vectors? What are the column vectors? So these are the column vectors. Right? I haven't talked about the dimensions, but these are the elements of which vector space? Belonging to? No, these are the elements of. You should know that this, if we consider this as a1 vector, a2 vector, a n vector. So these are elements of this vector space R n. Okay. Now, what we are considering in the column space of A. Column space of A is the linear combinations of these vectors A1, A2, An, of these vectors. Okay, when we are considering the linear combinations of these vectors which are in Rn, so that we are considering as CA. So this is a subspace that we have already proved. Okay, this is a subspace of Rn that we have already proved. How can we prove? We prove the general result, right? If so, this is the linear span of these vectors A1, A2, An. Right? So if this is the linear span of this CA is the linear span of this A1, A2, An, then this will be a subspace of Rn. So that's why you're saying that this is a subspace of Rn.